All right, welcome. In this video, we're going to take a look at some acid-base neutralization reactions and titrations. So first, let's review how hydrogens and hydroxides are related to the idea of being an acid or a base. Water has a formula of H2O. That's how we typically write it. It looks like this. This is what water looks like. We could also think of water as being made of, we can also write the formula like this, HOH. And if you think of it that way, that might help you see that when we have water, we have equal amounts of hydrogen and this other thing OH, which we call hydroxide. So OH minus, that is the hydroxide ion. So water is neutral and it contains equal amounts of hydrogen and hydroxide. By contrast, if something is an acid, when you put an acid in water, it's going to make extra hydrogen ions. So when you have an acid, you're going to have more hydrogen ions present in the solution. When you add a base to water, it's going to produce hydroxide ions. So with that information, we can identify these solutions, figure out whether they're an acid, base, or neutral, just by counting the ions present. Looking over here on the left, you might notice that this solution, it contains 2 hydrogen ions, and it contains 4 hydroxide ions. So this solution has more hydroxide than hydrogen, so this solution is going to be base. This middle solution contains 3 hydrogen ions, and it contains 3 hydroxide ions. So if the amount of hydrogen and hydroxide are equal, this solution is neutral. And then over here on the right, this solution contains 4 hydrogen ions, and then only 2 hydroxide ions. So this solution is going to be acidic. Okay. So now let's take a look at what happens if we mix together an acid and a base. So when we mix together an acid and a base, this type of reaction is known as a neutralization reaction. And the products of this reaction are going to be what we call salt and water. So here's an example. HCl is an acid. You might remember the way I can recognize that HCl is an acid is because its formula starts with hydrogen. Sodium hydroxide is a base. I can spot that because I can see that hydroxide, OH, and we know bases make hydroxide when we stick them in water. And I recognize this is water, H2O, that's water. So therefore, this other thing we made must be salt. And that is actually the definition of what is salt. It is the thing that is made in the reaction that is not water. So this is what we call salt. And there's a variety of different salts out there. You might look at that and say, oh yeah, I know that's salt. That's sodium chloride. That's table salt. That is the type of salt that we put on our food. But just so you know, there are other types of salt out there. So here are some examples of other things that are also called salts. K3PO4, MgSO4. There's lots of ionic compounds out there in the world that can also be considered salt. So just so you know, that's a general term that applies to more than one kind of compound here. All right, but let's keep that in mind. Let's try and predict the products of this reaction. So we've got here H3PO4, that is my acid. This right here looks like my base. And I know that when they react, they're going to produce salt and water. So I'm going to start out by writing out the formula for water. That's H2O. So notice how my hydroxide and my hydrogen combine to make water. So what's going to be my salt? It's going to be the other substances that haven't reacted yet. So my calcium and my phosphate are going to combine together to make the salt. Now I want to stop. Whenever I'm writing a chemical formula, I need to make sure that I have the subscripts correct. So is it CaPO4? Should there be a 2 here? Should there be a 3 here? Should there be a number over here? We got to figure out what our subscript should be. And you might remember from back when we did this in an earlier unit, the way that you figure out what the subscript should be is by looking at the charges. So I'm going to look at my periodic table for calcium because it's an element. I'm going to notice that calcium's over there in the second column. It's got a +2 charge. And then PO4, this is one of those things called polyatomic ions. You might remember that from earlier in the year. There's this table of polyatomic ions you can refer to. Phosphate, PO4, has a charge of -3. And then to figure out the correct formula, I'm going to do a little crisscross to make sure my charges balance out. So whatever number is over here, that's going to become the subscript over there. And then this number is going to become the subscript over there. And then that looks kind of messy, so I'm going to rewrite this. Okay, so I end up needing 3 calciums for every 2 phosphates. And with this, we're going to put a 2 here. Notice how we use parentheses, because notice how if we didn't have the parentheses, it would look like 42, right? We don't want it to look like 42, so that's why we put a parentheses around it if we've got kind of 2 sets of subscripts there. Okay, so that is my chemical formula. Now I want to balance it. Okay, so I'm going to put a little space here in the front so I can balance it. I'm going to start by balancing my calcium because that looks like the easiest one for me to try and balance. So I see there's a 3 there, so I'm going to put a 3 over here. And then you also have H2O. Sometimes when you're balancing, a trick here with this is instead of writing H2O, it can be helpful to think of this as hydrogen hydroxide. Because then you can look at this and you can say, okay, notice on the left, I have 3 times 2. That means I have 6 hydroxides over here on the left-hand side. So I'm going to need 6 hydroxides over here on the right-hand side of my equation. And with my phosphates, notice how I have 2 phosphates on the right, so I need 2 phosphates over here. And notice how 2 times 3, that gives me 6 hydrogens. And now I need 6 hydrogens over here, which check I already have. So perfect. Now my equation is balanced. So remember, balanced means you get the same number of atoms on each side. So I've got 3 calciums on the right, I've got 3 calciums on the left, I've got 6 hydroxides, 6 hydroxides, got 6 hydrogens, 6 hydrogens, and then what else? 2 phosphates. All right, so let's try this with another one. So H2SO4, that looks like my acid. This contains hydroxides, so it looks like my base. And then we're going to make salt and water. So my water is H2O, or I could write it as HOH. You can decide whichever thing I prefer. And then my other substances that aren't H or O, they're going to combine together to form my salt. So in this case, it's potassium and sulfate are my ions that are coming together. And as we're trying to find the chemical formula of these ions, I want to look at charge. So potassium's over there in column 1. It's got a +1 charge. Sulfate, SO4, that's one of my polyatomic ions. It has a -2 charge. So sulfate is -2. So when I do a little crisscross, the 2 goes down here, the 1 goes down here, but we just usually don't write 1. So now I'm going to go back and erase these, and there you go. That is my chemical formula. So notice how on this side I have 2 potassiums. Over here I only have 1. So I'm going to add in a coefficient here. I'm going to erase these things I circled. That's going to give me 2 Ks. Those are my potassiums. Now I have, and then remember when I'm balancing, it can help to rewrite this as HOH instead of H2O. So just keep in mind, you can write it either way. These mean the same thing. H2O, HOH, they're the same. All right, so it looks like I have 2 OHs. So I need to have 2 OHs over here. And then that'll also give me 2 hydrogens, which is great because I already have 2 hydrogens over here. So if I go through and check everything, it looks like we're all good. I've got 2 potassiums, 2 potassiums, 2 hydrogens, 2 hydrogens, 2 hydroxides, 2 hydroxides. And then the SO4, I've got 1 SO4 over here. I've got 1 SO4 over here. So I'm all balanced. All right. You might notice that another way to think of this type of reaction is it follows this pattern that we call a double displacement reaction, which what that means is your acid, you have your acid and your base. And in this double displacement style reaction, you can think of it as the first elements in each compound switch places with each other. So notice how the sodium, we can think of it as a sodium and the hydrogen switch places. So now the sodium bonds with the chlorine and the hydrogen bonds with the hydroxide. And hydrogen and hydroxide is otherwise known as water. So if you go back and take a look at these reactions again with this lens, that's another way to help you figure out what's happening in this type of reaction. It's like the calcium and the hydrogen swap places with each other, or the potassium and the hydrogen swap places with each other. So that's another way of thinking of this type of reaction, just as an FYI. All right, so now let's talk about a titration. So a titration, it's a process, so it's a laboratory process that you're going to do. And it's where you add a solution of known concentration to determine the concentration of another solution. So you have a known and you have an unknown. And when we titrate something, we're eventually going to reach what we call the equivalence point. Sometimes we also use the term end point of a reaction. And at the equivalence point, that's when the number of moles of your hydrogen ion is equal to the number of moles of your hydroxide ions. So in an acid-base titration, which is the kind that we're going to do, you're trying to figure out like how much acid does it take to neutralize your base, or how much base did it take to neutralize your acid. So we're doing an acid-base neutralization reaction here. So in other words, when you have reached your equivalence point, or the end point of your titration, when you have the same number of moles of your two reactants in your chemical equation. So, because your reactants are your acid and your base in this case. So let's kind of think through chemical equations and refreshing ourselves about how we can interpret these. So for example, question, how many moles of HCl will it take to neutralize 6 moles of NaOH? So you look at the balanced chemical equation and notice how they all have coefficients of 1. Remember, the coefficients are the number that are out in front. And if there's no number out in front, that means we assume that it's a 1. So we say they react in a 1-to-1 mole ratio. So every 1 mole of HCl needed for 1 mole of NaOH. Therefore, since the ratio is 1-to-1, it would take 6 moles of HCl to neutralize 6 moles of NaOH. So that's my answer. It would take 6 moles. All right. So with that logic, let's try a couple other problems. So how many moles of HCl would it take to neutralize 3 moles of NaOH? Well, I've got 3 moles of NaOH, and I know, so I'm going to write this out using dimensional analysis to see if this kind of rings a bell here. So I got 3 moles of NaOH, and I know that for every 1 mole of NaOH, I'm going to need 1 mole of HCl. They react in a 1-to-1 ratio. Therefore, I must need 3 moles of HCl to neutralize my base. Another way you might write it is you might say, 3 moles of NaOH is to X moles of HCl. And then I know that for every 1 mole of HCl, I need 1 mole of NaOH. So you can set it up like we call equivalent fractions here and try and solve for X. Do a little cross multiplying. Now let's look at an example where we actually have some coefficients here. So in this case, I want to figure out how many moles of NaOH it would take to neutralize 2 moles of H2SO4. So I've got 2 moles of H2SO4. And if I look at my mole ratio, it looks like for every 1 mole of H2SO4, remember if there's no coefficient, we assume that there's a 1 there. So every 1 H2SO4, I need 2 NaOHs. They react in a 1-to-2 ratio. So I need 4 moles of NaOH to react with my 2 moles of H2SO4. And then how many moles of H2SO4 would it take to neutralize 2.4 moles of NaOH? Well, it looks like for every 2 moles of NaOH, I need 1 mole of H2SO4. So I'm getting my mole ratio from that balanced chemical formula. So 2.4 times 1 divided by 2, that's 1.2 moles of H2SO4. And you can show your work in a variety of different ways, as long as you're, like if this were a problem on an assessment, you just want to make sure you show your work, or you can explain it out in words if you want instead. I'm just showing my work this way. You could use this way. You could write out a sentence saying because it is a 1-to-2 mole ratio if you want to. That's okay too. All right. So endpoint is remember I mentioned earlier that sometimes our equivalence point, we refer to that as the endpoint. So endpoint is really more of like an experimental term. It's when the point at which the solution changes color. And your solution might be an acid or a base, depending on how you have your titration set up. So when we're doing a titration, what we're going to have here is we have our solution down here at the bottom that is our unknown. We don't know the molarity of it. And then we are going to add your known solution to it. And so we're going to, and then once we figure out how many moles of our known solution it took to react with our unknown, we can figure out what our unknown was. So like in this example right here for E, it looks like we did a titration experiment. We found that it took 2.4 moles of NaOH to neutralize my sample of H2SO4. And based on this chemical equation, then we can figure out, well, that means there must have been 1.2 moles of H2SO4 in this container. So that's basically what we're doing. We're going to have a known amount, and then we're going to use that to figure out some unknown. So steps to doing a titration calculation. First, we need to know what the reaction is, we need to use those mole ratios. So step one is if you're not given a reaction, you got to write out a reaction. So we're going to, just like we did up here, we figure out what's the balanced chemical equation. All right. Step two, we're going to determine moles of our known. And these are going to be solutions. So we're going to be dealing with molarity. So a reminder that since molarity is moles divided by liters, I can rearrange that and say molarities times liters gives me moles. So if I know the volume and molarity, I can find how many moles I added. Then I'm going to use my mole ratio to figure out the moles of my unknown. And then once I know that, then I can figure out the concentration of my unknown. So these are the general steps for doing a titration calculation. And let's work through an example here. So first example, we're reacting HCl and NaOH. So first thing I'm going to do is I'm going to write out the neutralization equation. So HCl and NaOH, when they react together, I know I'm going to make water and I'm going to make salt. So my H and my OH will be used to make the water, and then what's left over is my Na and my Cl. Sodium has a +1 charge, chlorine has a -1 charge, so I don't need any subscripts there. So if I go through and double check, this equation is already balanced. I've got 2 H's, I've got 1 2 H's, 1 chlorine, 1 chlorine. Cool, it is all balanced. So everything is a 1-to-1 mole ratio. Cool. All right, next step, determine moles of your known. So notice how I'm given two volumes, right, 30 milliliters and 60 milliliters, but I'm only given molarity for one of these things. So NaOH, I have more information about. So my NaOH is what we call my known. So I know the molarity and the volume of my NaOH. So if I take my molarity, 0.2 molar, and then my volume is 30 milliliters, well, it's important to know that 1 liter is 1,000 milliliters. So to find out how many, liters is, I have to go like this, 0.03. So 30 milliliters is 0.03 liters. So don't forget to convert your milliliters into liters when you're doing this type of calculation here. So 0.2 times 0.03, this is 0.006 moles of NaOH. It's really important we label what it's moles of so we can keep track of whether we're talking about the acid or the base. So this is my known. My known is the base in this case. So now what I'm trying to find is what is the molarity of HCl. That's my goal here. So my next step is I'm going to take my moles of base and I'm going to use my mole ratio, which I get from the chemical equation, to figure out my moles of my acid. So it looks like they react in a 1-to-1 ratio. So for every 1 NaOH, you got 1 HCl. So if I have 0.006 moles of NaOH, that means I also have 0.006 moles of HCl present. Okay? And now let's convert that into molarity. So molarity is moles divided by liters. So my moles of acid is 0.006 moles. And then my volume, got to make sure I use the right volume because there's a couple different volumes floating around here. It looks like my HCl volume is 60 milliliters. So 60 milliliters is I divide it by 1,000 to get the liters. So that's 0.06 liters. Oh, okay, that's going to give me a nice round number. What's the molarity? It's 0.1 molar. So I've just used this data to figure out what the molarity of my acid is. This is my HCl. Let's look at one more example. We've got sodium hydroxide and chromic acid reacting. And you got 20 mils of chromic acid and find that it requires 35 mils of 0.3 molar NaOH to neutralize it. So if we look at our steps for a titration here, here's our 4 steps. Step 1 is write the balanced chemical equation. Notice how this one, they did it for us. Hooray! Cool, so this is already balanced for us. Step 2, determine the moles of your known. It looks like in this case, our known is sodium hydroxide. So I know the volume and I know the molarity. So that means I can find moles. So my molarity is 0.3. My volume is 0.035. You gotta convert that in my milliliters into liters. So 0.3 times 0.035. And I've got, that's 0.0105 moles of NaOH. All right, boom. Found my moles of known. Next step is I'm going to use my balanced chemical equation and the mole ratio to figure out my moles of my unknown. So I know I have 0.0105 moles of NaOH, and I know that for every 2 NaOHs, I need 1 H2CrO4. How do I know that? I looked here at the coefficients in the balanced chemical equation. And remember, if there's no coefficient, you interpret that as being a 1. Okay. So I'm going to take this, I'm going to divide it by 2. And this is what we did this is stoichiometry, right? We're kind of going back to our stoichiometry skills here. All right, and that is moles of our unknown. And then the concentration of our unknown, concentration we measure in molarity, which is moles per liter. So that would be my moles of my unknown, which is 0.00525. And then my volume is 20 milliliters, so 0.02 liters. So remember, always convert your milliliters into liters. And it looks like my molarity is 0.26. All right, so there are some examples talking through titrations. Hope that helped.